All right, thanks for watching. And today it's gonna get sizzling hot because we'll solve the heat equation. The heat equation in this case is ut equals kuxx. And what this represents, in some sense, is the temperature of a metal rod. Let's say here an infinite metal rod at position x and time t. In general, uxt will give you the temperature of this sizzling rod at position x and time t. And the interesting thing is, if you compare it to the wave equation, which is utt equals c squared uxx, you might be like, oh, there's just a little difference in t. It shouldn't make a big difference, right? Wrong. Because this equation, just like a genetic mutation, like an extra chromosome, is very different from this equation. So two really completely different things. So you think math is math, but it's not math. It's different math. Okay, that said, that does use, though, this wave equation to motivate things a little bit. Because how did we find solutions of this? We factor things out, and in particular, assuming, for instance, this c squared is 1, the way we did this, notice somehow the factor t squared minus x squared came into play. And in fact, we factored this as t minus x times t plus x with differential operators. And in fact, the solution was f of x plus t plus f of, I guess, x minus t. And again, with ct, if you replace it with c. Now, let me give you two explanations. There is two motivations of what I'm going to say. On the one hand, consider, let's say, ut equals uxx, and cancel out the u. Why not? And then we get t equals x squared, and then assume everything is positive, so x is square root of t, so x over square root of t is a constant. Which means somehow the value x over square root of t will come into play. And in fact, that's what we'll do. We'll guess that uxt equals v of x over square root of t. For some v that we want to find. Now, this was a silly explanation. Let me give you maybe a better explanation. Because it turns out, if u solves this equation, so does u of, I think, square root of ax, comma, square at. Okay. And that's because, notice, in this equation, you differentiate once with respect to t to get an extra a out, but you differentiate twice with respect to x to get square root of a times square root of a, which is a. In particular, again, here a was constant, but let's assume a is 1 over t. Then we get that, in theory, a u of x over square root of t, comma 1, should also solve this PDE. And again, it's just motivation. There's no reason this has to be correct. But notice, this is of the form v of x over square root of t. It's a function of x over square root of t. So this thing with this dilation invariance is actually not too nonsensical, except it doesn't work. If you plug this into the PDE, it won't work. And the reason is as follows. Suppose v is identically, function identically 1. Okay? Then u would be identically 1. But it turns out, for the solution that we'll talk about, we would like things to blow up. Which is scary, because in math you usually don't want things to blow up, but here it's a feature. So what we'll do, instead of guessing u to be v of x over square root of t, you guess u to be 1 over t to the alpha v of x over square root of t. Where we not only want to find v, but we also want to find alpha. because again, this is nice, it blows up. And again, we're not like evil to make things blow up, but it's a feature. And again, I'll explain later why. I hope I remember why. I hope I remember to explain it. So, in other words, uxt is this, and then plug this ansatz into our PDE. So ut equals kuxx. That becomes t to the minus alpha, v of x t to the minus 1/2, t equals k, t to the minus alpha, v of x t to the minus 1/2, xx. For this part, we have to use the Prada loop. So minus alpha t to the minus alpha minus 1, v of, if you want, x over square root of t, plus t to the minus alpha. Now, v prime of x over square root of t, and the derivative of that with respect to t, so x, and then minus 1/2, t to the minus 3/2, equals k, t to the minus alpha. And notice, if you differentiate with respect to x once, you get v prime times t to the minus 1/2. So if you do it twice, you get v double prime times t to the minus 1/2 times another t to the minus 1/2. So you get v double prime x over square root of t, and then basically t to the minus 1/2, t to the minus 1/2. Okay, so we get a bunch of terms. So again, we get minus alpha, t to the minus alpha minus 1v, and then plus x. So I guess, sorry, minus 1/2 x t to the minus alpha. Let's write like this: minus alpha minus 1 minus 1/2, and then v prime equals k t to the minus alpha minus 1 v double prime. Looks really scary, but notice this t to the a lot of the terms cancel out, yeah? This t to the minus alpha minus 1 all cancels out. And then we're left with something slightly easier. We're left with minus alpha v minus x over 2. T, so I guess x over 2 square root of t. Square root of t v prime minus k v double prime equals 0, which if you want, you can just write this as, with positive terms, k v double prime, okay, and then plus x over square root of t over 2 v prime plus alpha v equals 0. And here's a nice thing. So what is v prime? So here v equals vy, where y is x over square root of t. So v prime, what this is, it's dv over dy. Okay. Just to specify, the reason this is nice is because notice, this thing here is actually just y. So you get a much easier differential equation. K v double prime plus y over 2 v prime plus alpha v equals 0. But you might still be concerned because we started with this PDE and we kind of turned it into this really complicated differential equation. But two things. First of all, it's an ordinary differential equation. And ODEs are so much easier than PDEs. So even though this might be complicated, it's actually good, right? And another thing is we have something in a closed form. Because notice everything now depends on y. there's no more x and no more t together. It's simply really just an ODE with no extra variables. And by the way, this is why this choice of 1 over t to the alpha was important. If we didn't have that, we wouldn't get an ODE in a closed form. Now, on the other hand, we're still stuck because this is not a constant coefficient ODE, hard to solve. Well, it would be great if we had a 1/2 here, because at least we could factor out 1/2. But indeed we can, because notice we had some leeway on our alpha. We said alpha is to be found. So let's just let alpha to be 1/2. And this is the great thing about analysis. You always have those the parameters that you haven't defined yet, which makes the problem look complicated, but complicated problems actually lead to more freedom. Because now, even though this was more complicated with the alpha, now we have the freedom to choose which alpha we want. So again, just appreciate this, and then we had kv double prime plus 1/2 y v prime plus 1/2 v equals 0, and then we had kv double prime plus 1/2 yv prime plus v equals 0. And notice this is kind of the beginning of the Prada rule, right? So v prime y plus vy prime, which is the derivative of something, and indeed you can write that as a derivative. Kv double prime plus 1/2 yv prime equals 0. And what makes this even more amazing, you can write the whole thing as a derivative, because kv prime plus 1/2 yv prime equals 0. So what does that tell you? It tells you that kv prime plus 1/2 yv equals to a constant. But again, here's the thing. I'm not telling you let's find all the solutions. And in fact, there are like infinitely many solutions, some of which are not found by this method. We just want to find one solution. And in particular, again, we have the choice of our C. So let's just pick CB0. I know, it's very like, it should give you a calculus heart attack, but again, we're not trying to find all the solutions. Here in this video, we just want to find one solution. If you don't like this argument, you could also argue, well, assume in our physical problem that v prime and v go to 0 fast enough as y goes to infinity, then this goes to 0, then yv goes to 0 if v goes to 0 fast enough, and then you just get 0 equals c, so your constant is 0. And here's a nice thing. We started with this complicated second order ODE. In fact, we started with the second order PDE, which we found to be a second order ODE. And now we just have this first order ODE, which we can solve. So okay, so now what we have, so I guess kv prime plus y over 2 v equals 0. So in other words, v prime equals minus y over 2k. V. Remember y2k? 19 years ago, but it's a big thing. I thought this just meant like happy 2000, and I just sent greeting cards. Everyone was saying like happy Y2K. Anyway, so we have this first order ODE. We can just solve this. So v prime over v equals minus y over 2k. And then ln of v prime equals minus y over 2k. And then basically integrate ln of absolute value of v. It's minus y squared over 2k for 4k. So y squared over 2 over 2k. So 4k plus a constant, and then basically absolute value of y, it's e to the minus y squared over 4k, and then e to that constant. And lastly, this means v equals plus or minus e to the c, e to the minus y squared over 4k. And this, since c is a constant, plus or minus e to the c is also a constant, which means we finally solve for v. So what is v? V of y, it's c e to the minus y squared over 4k. And now we want to go back to u. Remember u was 1 over t to the alpha, v of x over square root of t. But now we chose alpha to be 1/2. Remember, freedom of choice. So 1 over t to the 1/2. And then c e to the minus x over square root of t squared over 4k. And if you do that, you simply get c over square root of t e to the minus x squared over t over 4k, so 4kt. For all the kt's in the audience, this is for you. Again, which gives us actually a family of solutions of the heat equation, but it turns out there is one choice of constants that makes this even nicer. I wore the wrong shirt for this. I should have worn my Gaussian integral shirt, because if you choose c to be 1 over square root of 4 pi, then we get u of xt. It's 1 over square root of 4 pi, 1 over square root of t, e to the minus x squared over 4kt. Sorry, 4 pi k. And then we finally get the fundamental solution. I explain why we have this constant. uxt is 1 over square root of 4 pi kt e to the minus x squared over 4kt. And this thing, it's called not the meh solution of the heat equation. It's called the fundamental solution of the heat equation. Oh, let me write a flame of the heat equation. Or sometimes called, I think, the Gaussian kernel or the heat kernel, whatever you want to call this, as long as you accept it. Just one little remark on the choice of constants. Why do you have this constant? Because with this property, this solution satisfies the integral from minus infinity to infinity of uxt dx equals 1. Because you can just do a change of variables, like p equals to x over square root of p equals x over square root of 4 pi or something, and then x over square root of kt, right? And then what do you get? X over square root of 2kt. There we go. And then what we get, basically, you do this u substitution, and then you get the Gaussian integral, which evaluates, I think, to square root of pi. And then, what do you want to say? Yeah, and that cancels out with the square root of pi here, and then the change of variables cancels out with the square root of 4kt. Therefore, you have this solution, and with this choice of constant, essentially the mass of the solution is preserved. So something that's interesting about this, and the reason why this is so important, is because what do those solutions look like? They look like Gaussian curves. Right? But then if as t gets larger, they get like more and more spread out. Something like that. But also, on the other hand, as t gets smaller and smaller, they actually just spike up. They might look like something like that. So it spikes up, all while the mass is 1. And in case you know it or don't know it, such a functional, not function, is what's called the Dirac delta function. The functional, okay? Because it's really, and this is why this Gaussian kernel is so important, because essentially as t goes to 0 plus, those fundamental solutions, they converge to the Dirac delta functional. And this is why, if you want, the formula with the initial conditions works, which I'll talk about next time. All right, so if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.